Last week we talked about experimental probability, and if you recall, we're going to kind of define some terms we haven't gotten to quite yet. Our first one is probability, which remember is the chance that an event is going to occur, which is that ratio of the number of favorable outcomes for an event to the number of total outcomes, which we can write as a fraction, a decimal, and a percent. Now, last week we talked about experimental probability being that it is what actually happened when an event was performed. Now, some of you started to get into theoretical probability, which we touched on last week on the quiz. Remember, theoretical probability is what should happen, what we want to happen if the world were perfect, but we know the world isn't perfect, so then we want to get into that experimental probability piece. So let's take a look at the first example, which is going to be that there are 6 red marbles, 8 blue marbles, and 2 yellow marbles, and 9 white, all in a bag, and we want to determine each of these probabilities that are listed below. The first step is going to be to determine the number of favorable outcomes in the event, what we want to happen. That second step will then be to determine the number of total outcomes. And then finally, step 3 is to set up the fraction, simplify it, and convert it to a decimal and our percent. So the first thing we want to look at when we are looking at our first example of the probability of a white marble. Now, if we take a look at this, we have 9 white marbles. So that means that our numerator is going to be 9. And then our total number of outcomes are the total possible marbles we have to choose from. So if I add these up, 9 plus 6 is 15, and 8 plus 2 is 10. So I know that I have 25 total marbles to choose from. Now, if I calculate this by taking 9 divided by 25 on a calculator, I'm going to get 0.36, which is equal to 36%. Now, primary color. If you've taken art class, you know that primary colors are red, blue, and yellow, which if we add 6, 8, and 2, we get 16, still out of 25. So then if I take this, I know it's 0.16 divided by 25, I know that that is 6.64, which will give me 64%. Now remember, this isn't what actually happens. This is what we would assume would happen if the world were perfect. Now, this final example is the probability of not drawing a red or a blue. So that means that anything but red or blue, which means we can draw yellow or white and fit into this criteria. 9 plus 2 is 11, and so it's still out of 25. If I take 11 divided by 25 in a calculator, I get 0.44, which is 44%, and you learned how to change those to decimals and percents last week. Now let's move on to the next type, which is taking a look at comparing experimental probability to theoretical. Here we have Lucy. She rolled a die, which would be singular for dice, 50 times and recorded her results. We want to compare her experimental probability to the theoretical probability. So the first thing that we're going to do is we're going to calculate our percentage for each experimental probability. Then we're going to calculate the percentage for each theoretical probability, and then finally compare it. So when I take a look at this, the experimental probability, that would be finding the probability of getting, and I'm going to put EP so I know I'm talking experimental, and then I'll do theoretical probability over here on the side so we can compare them. Now our experimental probability. If we talk probability of rolling a 1, that's going to be out of 50, 5 times out of 50, which would be 10%. The probability of getting a 2 is 4 out of 50, which would be 8%. The probability of getting a 3 is going to be, if you look at this, and I should scroll this back down for you, is 10 out of 50, which is 20%. The probability of a 4 is 8 out of 50, or 16%. The probability of getting a 5 is 12 out of 50, which is 24%. And the probability of getting a 6 is 11 out of 50, or 22%. Now, talking about theoretical probability. When we look at theoretical probability, in theory, we should have a fair chance of getting every one of these numbers the same amount of times, which would be a 1 out of 6 chance, which if you take 1 divided by 6, you get 0.167, or 16.7%. Now if we go ahead and compare those, we're going to get a comparison of it being pretty close. It varies, but I would make the comment to say that it's more likely that we're going to get a 5 or a 6 or a 3, because those ones are the highest ones. More likely to get a 3, 5, or 6 experimentally. Then because we say experimentally because that's compared to what they say. Now if we look at C talks about now Lucy rolled the die for a total of 500 times and recorded her results. So then if we look at this, I have that the probability of getting a 1 is now 82 out of 500, which if you take a calculator for that, 82 out of 500 is going to be 160 is going to be 0.164, or 16.4%. A probability of getting a 2 is going to be 83 out of 500, or approximately 0.166, or 16.6%. Probability getting a 3 is going to be 84 out of 500, or 0.168, or 16.8%. I apologize for my handwriting. I'm going to extend the page here. Probability of getting a 4 is going to be, again, 82 out of 500, which we know is 16.4%. Probability of getting a 5 is 84 out of 500 again. Remember, because I'm taking what I want to occur out of what total trials, 16.8%. And a probability of getting a 6 is 85 out of 500, which would equal 0.17 or 17%. Now if you take a look in comparison to up here when we recorded that theoretical of 16.7%, I would now have to say that our experimental probability and our theoretical probability, and I'll say EP for experimental probability and TP for theoretical probability, try that again, are more closely matched. Because now the percentages are relatively close together. What I want you to do now is go ahead and complete these two U-Try problems, bring them to class with you tomorrow so we can discuss them as a part of our day.